Chapter 6 is on circular motion. So we know from previous chapters that when an object travels in uniform circular motion, which means the speed is constant, but the velocity vector is not constant, and so it is accelerating, and it's accelerating towards the center of the circle with an acceleration called the centripetal acceleration, which is v squared over r, where r is the radius of the circle. Now, in order for something to go in a circle, you have to apply a force. So if you just imagine looking down on a puck that's sliding on the ice, so say it's just sliding along in this direction. If no force acts on it, it's going to carry on in that direction. But if you apply a force up on it, so you come along here and the force is up, well, that's going to make it start to turn up. And then once you let the force off, the thing would just continue in a straight line again. So if you want it to turn again, you have to push left, and that would make it turn left, and so on. You have to keep pushing and pushing and pushing towards the center of the circle in order for an object to go in a circle. There is no force out of a circle. It's in order to get something to go in a circle, you must push in. So Newton's second law for circular motion, which is F net equals ma. The F net now, you'll notice how this force is over here when this thing is going in a circle. The force is not just left, right, up, or down. It's always toward the center. And so the net force, it has to point toward the center of the circle. And then this becomes the centripetal acceleration. Now, the way I like to write this is in minus out equals mv squared over r. That's the working form of Newton's second law for circular motion. In means towards center, and out means away from the center. So as long as the towards is bigger than the away, the thing is going to go in a circle. And this is away from center. Okay, so the examples that you're going to get are like a ball on a string. So say you have this ball that's being twirled in a vertical circle on a string. Remember, strings only pull, so the force of tension is always pulling on the ball, whether it's at the top of the swing or the bottom of the swing. Now, the force of gravity is always acting, always down. So even if it's up here, the force of gravity is down. And you can see when you're at the top and when you're at the bottom, the in and outs are different. So when you're at the top here, the in forces are the force of tension and the force of gravity. That's in. There's nothing out. And so that's mv squared over r. But when you're down here at the bottom, you've got the force of tension in, and you've got the force of gravity out. And so then there's Newton's second law. And those are different. And so the tension, these two are different tensions. And clearly, at the bottom, the tension is bigger. And if the string is going to break, that's where it's going to break. It's down here at the bottom. Now at the top, you could have this tension force go to 0. If you swing at just the right speed, this speed, which would be like the minimum speed, V min, would be root r times the force of tension over the mass. And that's the minimum speed you have to swing a ball vertically at in order for the string not to go slack at the top. Okay, so those are some examples of circular motion that you're going to come across in your mastering physics. Now, another one is going to be a car just driving around on a flat road. So if this car, imagine it's going around in this circle. It's kind of hard to draw this. The force actually that makes the car turn the corner is friction. So you turn the wheel to the left and just imagine the tires kind of kicking over to the right, pushing on the road. The road pushes back left and makes the car turn left. And so the in force is friction. There's nothing out. And so that must be mv squared over r for a car turning a corner. And that's not a banked road. This is just a flat, whoops, corner. This is just a flat road. Now the force of friction, if it's on a flat road, is mu Fn. And Fn on a flat road is mg. So the equation for a car turning a corner on a flat road, doesn't even matter what the mass of the car is. The coefficient of friction times gravity is equal to v squared over r. So that's very handy for cars driving around on horizontal level roads. Okay, now you have the case of a roller coaster. I should do this one. Car on level ground. And then this is ball on a string, this one up here. So you'll have questions on mastering physics about each of these situations where objects are undergoing uniform circular motion. Okay, now the roller coaster, that's when you go upside down. So when you're at the top, you're upside down. And when hopefully you have a strap on so you don't fall out. But if you're going fast enough, you don't even need the strap. And then at the bottom, you're right side up. And this is the radius of the circle. And your speed, let's assume we're going around like this. Doesn't matter which way you're going around. Okay, so what are the forces on you at the bottom? Well, you've got the normal force. You're sitting on the seat. And so if you were sitting on a bathroom scale, the normal force would be your apparent weight. So questions that say, what is the apparent weight of the person in the roller coaster at the bottom? What they're asking for is the normal force. And then you've got gravity. Now up here, if you're going fast enough, the seat is still keeping you from falling through it. So you still have Fn, but you also have Fg. And so this is similar to the string. At the top here, you have the normal plus gravity is mv squared over r. There's nothing out. At the bottom, though, you have in minus out is mv squared over r. Okay, and so now the normal force is what's going to be different on the top and the bottom. And the normal force, often they're going to say, what is your apparent weight? And that's what they mean. Because if you were sitting on a bathroom scale, it would be what the bathroom scale would read. Now, a Ferris wheel is different. A Ferris wheel, you don't go upside down. And so you're sitting upright at the bottom, but up here also sitting upright up here as well. And so when you're in a Ferris wheel, then the normal force is always up and gravity is always down. But they play different roles because at the bottom here, the in is the normal. And so potentially this normal at the bottom could be bigger. In other words, your apparent weight would be more. You'd feel heavy at the bottom. But at the top, the in is gravity and the out is normal. They're switched. Now the normal can easily go to 0 here. If you're going just at the right speed and you go flying over the top of in this Ferris wheel, no, they never go that fast, but if you went really fast, you could drop this normal to 0, in which case the max speed, so you don't fly off the seat up there, would be Fg times r over m. And that would be the biggest speed you could have without flying up off your seat. Okay, and then there is the car on a hilly road, not turning a corner, but just driving up and down. Whoops, hilly. I don't know why I keep putting it G, hilly. I don't know how to spell hilly. Anyway, hilly road. Okay, so this would be the cars driving around like this. So here you are going over the top of a hill, and then when you're down here, you're in a valley. And you're going down along like this. And then here, this would just be level ground. Now you always have the normal force, and you always have gravity in every case. And they don't change direction. The car doesn't go upside down or anything. However, your circular motion here is different. When you're at the top of a hill, it's like being in the Ferris wheel at the top of the circle. There's your circle. You don't have to go all the way in a circle to be in circular motion. As soon as you start just going across an arc like that, you are in circular motion. And the in minus out here is gravity minus the normal is mv squared over r. This is like being on the top of a Ferris wheel. It is possible for the normal to go to 0 here. This is when you just kind of lift off your seat if you drive fast enough. Whereas this one, this is the circular motion. There's no way you can lift off your seat. You can feel really heavy here. The normal is in, gravity is out. And so this normal is going to be bigger than gravity. You have to have a normal. You can't have a negative number equal mv squared over r. It's all positive. Here, there's no circular motion. The normal equals gravity. Okay. So those are the physical situations you're going to come across doing problems on Mastering Physics for this chapter. Some other quantities that you're going to come across for circular motion that you may need are the speed is the distance around the circle over the time it takes to go around the circle. The distance around a circle is its circumference, 2 pi r, and the time gets a fancy name called the period. It's called the period of motion. And it equals the time to go around the circle once. Circle. So that's a very handy equation that comes up. And then frequency is often also defined here. Frequency is 1 over the period. And so this is the frequency of the circular motion. And that would be measured in hertz. Those are cycles per second. And then there's angular frequency as well. That's omega. And that's 2 pi f. And so this is called angular frequency. And it's in rads per second. So 2 pi rads times hertz, which hertz is the same as a 1 over second. Sometimes you see that as second to the minus 1. That's the same as a hertz. And the 2 pi rads times 1 over second, that's how you get these rads per second. And rads are really funny. They kind of come and go. They're not a real unit. They're very tricky that way. Okay, so that should do for this chapter.